So in this video, we're going to review quickly electron configurations, things that we talked about in class, and we'll extend that to something called orbital diagrams. Both of these things are sort of like the Bohr diagrams of the new model of the atom. A Bohr diagram was a picture that showed us where all of the electrons were in an atom. Electron configurations tell us the same thing, but in a more algebraic way with the new model of the atom. Orbital diagrams will communicate the same thing that electron configuration does, but in a more pictorial way, and it throws in a little bit of extra information as well. So just on the left here, we see pictures of orbitals. Let's just quickly review. So when you're on the first energy level within the atom, this would be like on the first orbit in a Bohr model, the new model says there is only one sublevel in that first energy level. We refer to it as the 1s sublevel, and that sublevel has one orbital, a 1s orbital. The 1s orbital is spherical, the nucleus is at the center. An electron that's in the 1s orbital is flying around the nucleus in that spherical region of space. So on level 1, there's this one sublevel, the 1s sublevel, and it has one orbital, the 1s orbital. Now you recall that the Pauli exclusion principle, told us that each orbital in an atom, principle, can hold a maximum of 2 electrons, and those 2 electrons would have opposite spins. So if the first energy level has just this one 1s orbital, then that 1s orbital can hold 2 electrons. So the first energy level has 2 electrons, and then it's full. Now when you get to the second energy level, there are now 2 sublevels. So on the second energy level, you will find a 2s sublevel, which will have a larger spherical 2s orbital, just like the 1s sublevel had a 1s orbital. But on level 2, you'll also find a 2p sublevel. And the 2p sublevel has 3 orbitals. We call them 2p orbitals, or just p orbitals. And they look like these peanut-shaped orbitals. They're oriented perpendicular to each other, one on an x-axis, one on a z-axis, one on a y-axis, and the nucleus of the atom would be at the center, the origin. So notice that on the second energy level, there are now 2 sublevels. In the first sublevel, the 2s, there's only one orbital, the 2s orbital. And as we just said, the Pauli exclusion principle tells us that that orbital can hold 2 electrons and it's full. The 2p sublevel has 3 orbitals, and each of them, according to Pauli's principle, can hold 2 electrons. So in the 2p sublevel, you could have up to 6 electrons. There's 3 orbitals times 2 electrons each. If you add up all those electrons, you find that on the second energy level, you could have up to 8 electrons, and then it's full. Now, when you get to the third energy level, you're going to find 3 sublevels. You'll find a large 3s orbital, the same shape, like a sphere, but larger than the 2s and larger than the 1s. You'll find another 3p sublevel, another set of these peanut-shaped orbitals, and there'll be 3 of them. They'll be larger than the ones that were on level 2. But now you'll also find a 3D sublevel. The 3D sublevel has 5 orbitals in it, as you can see here. Those 5 orbitals are strangely shaped. It's getting hard to describe them. 4 of them, I'll just highlight them, this guy, this guy, this guy, and this guy, they have 4 lobes to them. They kind of look like 4-leaf clover plants. And then there's a weird one, the 5th one, which kind of looks like a p orbital with 2 lobes and a donut around the middle. You should just recognize they mostly look like those 4-lobed orbitals. So there's 5 of them. So you're seeing a pattern develop. On the third level, we have 3 sublevels. On the second level, we had 2 sublevels. On the first level, we had one sublevel. The s sublevel always has one orbital. The p sublevel always has 3 orbitals. And now the d sublevel always has 5 orbitals. You see a pattern there as well. Each of these orbitals, according to Pauli's exclusion principle, can hold 2 electrons. So you can have 2 electrons in the 3s. You can have 6 electrons in the 3p. And you can have up to 10 electrons, 5 times 2. You can have up to 10 electrons in the 3d sublevel. So in level 3, if you add all that up, you can have up to 18 electrons. And then finally, when you get to level 4, I say finally just because with all of the elements on the periodic table, when they're in their ground states, you don't need anything more than level 4. If there are excited states, then yes, you can go to level 5 or 6 or higher. But for ground state elements on the periodic table, we only need levels 1 to 4 to describe all their electrons. So on the 4th level, you're going to find 4 sublevels. There will be a 4s sublevel, which will have a 4s orbital, a very large sphere. You'll have a 4p sublevel, which will have 3 p orbitals. They'll be very large peanut-shaped orbitals. You'll have a 4d sublevel, which will have 5 4d orbitals. They'll be larger than the ones that were on the third energy level. And then for the first time, you'll have a 4f sublevel, and it, as you can count there, will have 7 orbitals. So notice there's 1 4s orbital, there's 3 4p orbitals, there's 5 4d orbitals, and now there's 7 4f orbitals. And you notice those are just consecutive odd numbers, 1, 3, 5, 7. When you get to level 5, you'll have a 5s, a 5p, a 5d, a 5f, and then you'll start going alphabetically. You'll say there's also a 5g, and the 5g would have 9 orbitals in it if you needed level 5. Now, each of these orbitals, according to Pauli's exclusion principle, can hold 2 electrons. 2 electrons in the 4s. You can have up to 6 electrons in the 4p sublevel. You can have up to 10 electrons in the 4d sublevel because there are 5 orbitals. 5 times 2 is 10. And you can have up to 14 electrons in the 4f sublevel. 7 orbitals times 2 electrons each. That adds up to 14 electrons. So then just some quick things to notice. If you didn't write these down in class, you're going to want to write them now. So the letter N in this new model of the atom, we know it represents the energy level of the electron. So N tells you the energy level that you're talking about, level 1, level 2, level 3, etc. But N also tells us the number of sublevels that are on an energy level. So pause and write that down if you haven't got it already. But what does that mean? It means that if you're on level 1, when N is a 1, there's only going to be one sublevel, the 1s. If you're on level 2, there will be 2 sublevels, 2s and 2p. When you're on level 5, let's jump ahead, there will be 5 sublevels, 5s, 5p, 5d, 5f, and alphabetically now 5g. So you can see that N is telling us how many sublevels are on each energy level. Now, N squared, if you take the value of N and square it, this will give you the number of orbitals that are in a given energy level. So pause and write that down if you need to. But what does this mean? When you're on level 1, when N is a 1, 1 squared gives me 1. So on level 1, there's only going to be 1 orbital, and that's the 1s orbital. But if you're on level 2, energy level 2, the n is equal to 2. So 2 squared gives me 4. So there would be 4 orbitals in energy level 2. Which are the 4 orbitals? Well, one of them is the 4s orbital, the 2s orbital, and the next 3 are the 2p orbitals. Right? So there's 4 orbitals total on level 2. When you get to level 3, 3 squared, there will be 9 orbitals. What are the 9 orbitals on level 3? Well, there's 1 3s, there's 3 3p orbitals, and there are 5 3d orbitals. 5 plus 3 plus 1 is 9 orbitals in total. So you can see that n squared is giving us the total number of orbitals on each energy level. But Pauli's exclusion principle told us that each orbital can hold a maximum of 2 electrons. So if there are n squared orbitals, and each one can hold 2 electrons, 2 times n squared must give us the maximum number of electrons that are on each energy level. So pause and write that down if you have to. So 2n squared is the maximum number of electrons in a given energy level. If you're on energy level 3, 2 times 3 squared is 2 times 9. There will be 18 maximum electrons in energy level 3. All right, so those are 3 important things to notice. Now we saw that the periodic table can be divided into blocks, into blocks. The 4 blocks match the S, P, D, and F sublevels that we've been talking about. The first 2 columns of the periodic table, the alkali metals and the alkaline earth metals, grade 11 chemistry, as well as hydrogen and helium, those are referred to as the S block of the periodic table, the S block. The last 6 columns on the periodic table, what's green here in this diagram, those are referred to as the P block of the periodic table, the P block. The transition metals, the middle section, there are 10 elements in each row. Those represent the D block, S, P, D. And then the section at the bottom of the table, there are 14 elements in each row of that section. That's the F block of the periodic table. So S, P, D, and F, the different blocks on the periodic table. Now, the numbers in front of each letter in this diagram represent energy levels. So if you notice for hydrogen and helium, the first 2 elements, you're not only in the S block, you're in the 1s level within the atom. Their electrons are filling the 1s energy level. When you continue, you get lithium and beryllium, which are here, I'm highlighting on the left. Lithium and beryllium, they're in the 2s. So their last electrons are filling up the 2s sublevel. When you go from boron across to neon, those elements, those 6 elements, are filling up the 2p sublevel. And you could keep going. But if you notice a little pattern, when you have elements in row 1, hydrogen and helium, those were filling up 1s. Elements in row 2, from lithium right across to neon on your periodic table, they're filling up the 2nd energy level. When you're in the 3rd row of the periodic table, the 3s and the 3p, you're filling up the 3rd energy levels for the S and the P blocks. So you'll notice that whenever you are in an S block or a P block, whenever you have an element in one of those blocks, the energy level is the same as the row number on the periodic table. When you are in the 5th row of the periodic table, you are going to be filling the 5s and the 5p, right? But something different happens when you're in the D block. Notice that in row 5, when you get to the D block, you're not filling up the 5D, you're filling up the 4D. So in row 5 of the periodic table, the D block there is 4D. In row 4 of the periodic table, the D block is 3D. So you'll notice that when you're in the D block, if you have an element in that section of the table, it's filling up the energy level 1 less than the row that it's in. In the 4th row, it's the 3D that's being filled up. In the 4th row, in the 5th row, it's the 4D that's being filled up. So notice that pattern. Now, we saw this earlier in our notes, these energy levels of the different sublevels, and we remember the Offbow principle. Offbow principle. Okay, if you don't remember this, you can pause and write it down as I describe it. The Offbow principle told us that when you're filling energy sublevels, you start with the lowest energy sublevel, the 1s, and you build up. That's what the Offbow principle means. Start filling the lowest energy level and build up. In other words, fill them up from the lowest energy level. So you would start with level 1s, then you would go to level 2s, then you would go to level 2p, sublevel 2p, then to sublevel 3s, then to sublevel 3p, and after sublevel 3p, you would go to sublevel 4s, then to sublevel 3d, and then to sublevel 4p. You start at the bottom and you go up. Now notice that if you look at a periodic table, okay, look at the top table there, we were supposed to begin filling the 1s because it's the lowest sublevel. Well, 1s is the first 2 elements on the periodic table, hydrogen, helium. Then you fill up 2s. Well, 2s is what comes after hydrogen and helium on the periodic table. Then you fill up 2p. Well, 2p comes next on the periodic table. So you can see that if you know where the different blocks are on the periodic table, you don't need this energy level diagram on the right. When you're finished filling 2p, you're supposed to fill 3s. And look at this, 3s comes after 2p. When 3s is filled, you fill the 3p. When 3p is filled, you go to 4s. And then look at this. When 4s was filled, look at the diagram on the right. When 4s was filled, you're supposed to then go to 3d. Well, look at the periodic table. When 4s was filled, then comes 3d. And when 3d is filled, then comes 4p. So you can see that the way we understand the Offbow principle, starting filling orbitals at the lowest energy level and building up, that comes right out of the periodic table if you recognize all the different sublevels and the different energy blocks. If you know where they are on the periodic table, you don't need to know that diagram on the right-hand side of the slide here. So let's jump in and do some electron configurations. So let's begin with the simplest element, hydrogen. Hydrogen is the first element on the periodic table. It has just 1 electron. Its atomic number is 1. You can see that on the periodic table. If it has only 1 electron, I'm going to go over to the energy diagram on the right-hand side of the screen. The 1 electron can go in the 1s orbital, and we're done. So hydrogen's 1 electron is in the 1s sublevel in the 1s orbital. So we're going to say 1s, that's the sublevel that it's in, has 1 electron. So the 1 up here is telling me 1 electron in the 1s sublevel. That's what that means. Now let's go to helium. Helium is element number 2 on the periodic table, so it has 2 electrons. Where would they be? Well, looking at the energy level diagram on the right, the lowest energy level was 1s, the lowest sublevel, and it has 1 orbital. The Pauli principle tells us that 1 orbital can hold 2 electrons. So helium's 2 electrons are going to both be in the 1s sublevel. So our electron configuration would be 1s2. Right? So these things that I'm drawing, 1s1 and 1s2, those are electron configurations. That's what that means. So the electron configuration is telling us where the electrons are found, in which sublevels are they found within the atom. So let's jump to something a bit more complicated. Let's go to nitrogen over here. Nitrogen on my periodic table is element number 7. So this is going to be the last time I'm going to use this energy level diagram. Nitrogen has 7 electrons. Where can they go? So look on the right-hand side of the screen at our energy level diagram. We're going to put 7 electrons in there. We can put 2 of them in the 1s sublevel, and it's now full. It only holds 2 electrons because there's only 1 orbital. Then the next 2 electrons can go in the 2nd sublevel, the 2s. So there's 4 electrons total. But nitrogen had 7 electrons. The next 3 electrons are going to go 1 each into the 2p sublevels. So the 2p sublevel will end up having 3 electrons there. 2 in the 1s, 2 in the 2s, and 3 in the 2p, and there are the 7 electrons for nitrogen. So now we can say that nitrogen's electron configuration would be 1s2, because there's 2 electrons in the 1s sublevel, 2s2, there are 2 electrons in the 2s sublevel, and 2p3, there are 3 electrons in the 2p sublevel. There's the electron configuration for nitrogen. Now I said that's the last time I'm going to look at the energy level diagram on the right, because I can see the same thing if I understand the blocks. If I know the first 2 columns are the S block, the last 6 are the P block, the middle is the... If I know that, I don't need this energy level diagram. For example, when I look at my periodic table, boron is the first element in the P block there, then carbon, then nitrogen. Those are the first 3 elements in the 2p section of the periodic table. If you want to know nitrogen's electron configuration, the one that we just did, what you do is you start over at hydrogen, and you simply walk your way across the periodic table from hydrogen until you get to the element you're talking about, in this case, nitrogen. So let's take a walk. We're going to go hydrogen across to helium. That's 1s, and there's 2 elements there, hydrogen and helium. So because there's 2 elements, we'll say that's 1s2. Then we're going into the 2s block. And again, there's 2 elements there. So by the time we hit the 2nd element, which is beryllium, that's going to be 2s2. 2s because it's the 2s section of the periodic table, 2s2 because we walked through 2 elements, lithium and beryllium. Then we're going into the 2p section, so we write 2p, and nitrogen is the third element in. Boron, carbon, nitrogen. It's the third element. So we're going to say 2p3 because nitrogen was the third element. All right? So now, can we do the same thing by just looking at a normal periodic table? Okay, if you're just looking at a normal periodic table, you have to keep in your head this information. You have to keep in your head where the different blocks are and how the row numbers match the energy levels. So let's try this. We're going to write the electron configuration for, how about we do fluorine? Okay, fluorine is F. On your periodic table, if you have one in your data booklet, open it up. Fluorine is element number 9. You can pause if you need to get your periodic table out. So let's walk from hydrogen to fluorine. So I remember that hydrogen and helium, that's the 1s section of the periodic table. So that's going to be 1s2. Because there's 2 elements, hydrogen and helium. Then I know the 2s section comes next, and there's 2 elements there, so 2s2. Then I know the 2p section comes next, and we got to walk across to fluorine. So to get to fluorine, we walk through 1, 2, 3, 4, 5 elements to get to fluorine, so 2p5. So there's my electron configuration, 1s2, 2s2, and 2p5. Fluorine has 2 electrons in the 1s sublevel, 2 electrons in the 2s sublevel, and 5 electrons in the 2p sublevel. So can you do the same thing? This time you can pause the video and see if you can do the same thing for phosphorus. Element P, which is element number 15 on your periodic table. Can you pause the video and see if you can do the same thing? All right, so to get to phosphorus, we need to start with hydrogen and helium. There's the 1s section of the periodic table, 1s2 because there's 2 elements. Then comes 2s, we went through 2 elements, so 2s2. Then comes 2p, boron right across to neon, there are 6 elements there, so 2p6, we're at neon right now on the periodic table. Then after 2p comes 3s, and in order to get to phosphorus, we have to go all the way through 3s, so we'll say 3s2. We're now at magnesium. After 3s comes 3p, and phosphorus is the third element in that section, so it'll end in 3p3. So there is phosphorus's configuration. 1s2, 2s2, 2p6, 3s2, and 3p3. Phosphorus has 3 plus 2 is 5, plus 6 is 11, plus 2 is 13, plus 2. There are 15 electrons total, and we've described where they are in the different sublevels. That's the electron configuration for phosphorus. All right, so let's see if you could do something a bit harder. What about manganese, which is element number 25? And how about bromine, which is element number 35? Can you pause the video and write the full electron configurations for manganese 25 and bromine number 35? Look at your own periodic table to help. Okay, so for manganese, I can look and see that manganese is in the D block of the periodic table. It's in row 4. It's in the 4th row of the periodic table. And I remember that when you're in the D block, the energy level is 1 less than the row you're in. So if you're in the 4th row, manganese is going to finish with 3D. That's what it's going to finish with. And it's the 5th element in that section. Scandium was the 1st, titanium the 2nd, vanadium, chromium, manganese. It's the 5th one in. So manganese will end in 3D5. So let's walk our way across. Hydrogen and helium, 1s2. We've arrived at helium. Lithium and beryllium, 2s2. We've just arrived at beryllium on the periodic table. Then from boron, we go to neon, and that's 2p6. We've just arrived at neon on the periodic table, element Ne. Then comes 3s and 2. That's now going to be magnesium. We've arrived at Mg on the periodic table. After 3s comes 3p. We have to go all the way through it, so 3p6. We're now at argon on the periodic table. 4s2. 4s, we're now at calcium on the periodic table. And then to get to manganese, we have to go to 3D, and manganese is the 5th element, so 3D5. There is manganese full electron configuration. Bromine, if you haven't done it, pause the video and try. So for bromine, 1s2 helium, 2s2 and 2p6, we're at neon. 3s2 and 3p6, I'm at argon. And now going into the 4th row, 4s2, there's calcium. 3d, we have to go all the way through, so 3d10, there's 10 elements there. That's now zinc. And then we're going back to 4p, and bromine is the 5th element into that section, so 4p5. There's the bromine electron configuration. All right? Now that is kind of getting tedious. They're very long when you get to larger elements. There's a shortcut. So if you're asked for the full electron configuration, that's what you need to write. But we can also write what's called a noble gas abbreviated or shortened configuration. So this is a shortcut. We won't have to write everything we just did. If you listened to my explanation just a minute ago, go back and look at bromine. I said 1s2, I said we've arrived at helium on the periodic table. I hope you understand what that means. Then I said 2s2 and 2p6, we've arrived at neon. Notice helium and neon on the periodic table, those are referred to as noble gases. In grade 11 chemistry, that's the noble gas family of elements. So first, 1s2, we got to helium. 2s2 and 2p6, we got to neon. We're talking now about bromine. Now, if you find bromine on your periodic table, bromine is in the 4th row. Okay, it's a halogen. If you talk grade 11 chemistry, there's bromine. What was the last noble gas before we reached bromine? The last noble gas. Remember, the noble gases are in this last column. So the last one before bromine was argon. Argon would have ended in 3p6. So when I look at this full configuration for bromine, everything up to 3p6, all of this is really just argon, right? That's the last noble gas before bromine. So rather than write all that out, here's what we would do. We would say that bromine's noble gas abbreviated configuration, we would say it's equal to argon's configuration. So we put the symbol for argon in square brackets. Then we just add on the last bit. We add on the 4s2, the 3d10, and the 4p5. So there's the abbreviated configuration for bromine. Can you do the same thing? Let's pick a different element. Can you do the same thing for, let's pick something a bit simpler and then harder. How about rubidium? Can you do rubidium, element number 37? And then can you do, how about tin, which is element number 50? So rubidium, number 37, and then tin, number 50. Can you pause the video and try to write out their noble gas abbreviated configurations? Okay, so rubidium, the last noble gas before rubidium was krypton. So I'm going to say that rubidium is simply krypton's configuration with what extra? Well, what would come after krypton? Well, to get to rubidium, it's in row 1, 2, 3, 4, 5. It's in the 5th row. It's in the S block. It's the first element. So because it's in row 5 of the S block, we'll say 5s, and it was the first element. So 5s1. Now, what about tin? Tin is also in the same row as rubidium, so krypton was the last noble gas again. To get to tin, we have to go through the 5s sublevel. Then we have to go through the 4d, right? The 4d. And there's 10 of those, so 4d, 10, and 5s2. Then we go back to 5p. Okay, tin is in the P block in row 5, so 5p. And it's the second element, so it's going to be 5p2. Right? So noble gas abbreviated configurations. Now, one last thing. Can you give me what you would think is the noble gas configuration for chromium and also for copper? Okay, pause the video and write out the noble gas abbreviated configurations for those two elements. Okay, so chromium is in the first row, so is copper, of the transition metals. It's in the first row of the 3D block. So the last noble gas would have been argon, Ar. So we'll say chromium, we would think, is argon 4s2 and then 3d4. It's the fourth element in the D block. Copper, you would have thought, was argon 4s2 and 3d9. That's what you would think. I hope you understand that. If that's what you understand, well, I've got some bad news. This is wrong. Okay, now you're a little frustrated because you thought you understood what you were doing. These two elements, chromium and copper, are exceptions to the rules we've been outlining. Okay, something funny happens with these two elements. Later on in the periodic table, when you get to lower down elements, there are more and more exceptions. But up to krypton on the periodic table, up to element 36, these are the only two that are exceptions to what we've been learning so far. Something funny happens. The 4s orbital, the 4s sublevel, looks like it should have 2 electrons for both of them. Well, if you recall that energy level staircase that we talked about, the energy level staircase, you remember that the steps get closer and closer together. So n equals 1, n equals 2, n equals 3, the steps are getting closer together. Well, because of that, some weird things can happen. Where we should have had 2 electrons in the 4s step of our staircase, one of those 2 electrons decides it's going to move into the higher step. So one of those two electrons moves into the 3D sublevel out of the 4s. So that means instead of 4s2, you're going to end up with 4s1. So chromium is actually 4s1. It lost one of those two electrons from the 4s sublevel. Where did it go? It went into the 3D sublevel. It moved up a little tiny step on our staircase. So instead of 3D4 like we thought, it's going to be 3D5 instead. The same thing happens to copper. The very same thing. So copper, instead of being 4s2 like we thought, turns out that it's 4s1. One of those two electrons moves out of the 4s sublevel and into the 3D sublevel. So the 3D, instead of 9 electrons, it ends up with 10 electrons instead. So these are the exceptions that you must know. There's only 2, so you can guess I'm probably going to ask you about them on a test, or if we have one, on an exam later on. These are the only 2 exceptions that you need to worry about. All right, so if you're asked for chromium or copper electron configuration or noble gas configuration, you have to remember this little trick. One of the 4s electrons moves into the 3D sublevel. So I'm going to pause there. That's everything we've done in our third lecture on the quantum mechanics model. In a separate video, I'll talk about the orbital diagrams as well as a couple of other things.